Miguel, thank you very much. It's a real honor and pleasure to be here at this celebration of and conference for Barry. Barry and Gretchen's friendship has meant so much to me ever since I was an undergrad. I took a number of courses from Barry right here in this building. Lots of joyful memories from those classes. What was memorable to me is not the mathematics that he taught, but actually the poetry. We all know as mathematicians here that mathematics is beautiful, but sometimes when we're a mathematics student and there's some particularly messy sounding theorems and proofs, it helps to be reminded. And Barry always made sure not to just tell us that a theorem was beautiful or that a proof was beautiful, but why it was beautiful. He always spent a lot of time in a conversation explaining why it was beautiful, and that made all the difference in our classes. Barry was also my senior thesis advisor, along with Percy, and that senior year for me was very pivotal in my life, in large part due to Barry and Percy's advice that year, not on mathematics again, but because of their encouragement about being able to keep up subjects outside mathematics, in the humanities, while doing mathematics. They were so active in literature and poetry and philosophy and magic, and for me that was a great source of encouragement in knowing that I should also look for connections across subjects and the beauty across subjects, mathematics as well as the humanities and the connections among them. And so that year I decided to go to mathematics grad school, even though my interests lay in large part in the humanities. And since then, it's been a passion of mine to get more students interested in mathematics through the humanities. The reason it happened to me is that my grandfather was a scholar of Sanskrit, and so I grew up learning Sanskrit poetry, which is something I shared with Barry a lot when I was an undergraduate, and he was beyond encouraging in keeping that up. And so we heard today there are lots of connections between mathematics and poetry. Professor Scarry talked about how counting plays a very important role in composing poetry. But what's not as well known is that a lot of fundamental mathematical discoveries actually have their origins in the composition of poetry. The counting that comes from poetry led to important mathematical theorems that were first discovered in the context of poetry. And so that's what I want to talk about today, mathematics as it relates to poetry, as it first arose from poetry. So let me begin by telling you the setup of Sanskrit poetry. So this is how I personally became interested in mathematics. A lot of what I learned about mathematics growing up was what I learned from my grandfather about the rhythms of Sanskrit poetry. So let me begin by saying something about the setup of Sanskrit poetry and what makes it so mathematical and what lends itself naturally to mathematical questions. So just like many languages, poetry in Sanskrit has a notion of stressed syllable and unstressed syllable. But Sanskrit takes it a little bit further. A stressed syllable is called a long syllable. An unstressed syllable is called a short syllable. The reason being that a long syllable is actually longer than a short syllable when you pronounce it. In fact, a long syllable in Sanskrit is exactly twice as long when you pronounce it as a short syllable. So when you read Sanskrit poetry, a long syllable lasts 2 beats of time. A short syllable lasts 1 beat of time. And with that simple setup, you can imagine the kinds of mathematical possibilities and questions that immediately arise when it's not beyond just being stressed and unstressed, but it's long and short, where a long is 2 beats, a short is 1 beat. So the simple setup leads to numerous mathematical questions, which the ancient poets These questions came up for them, and they analyzed them in great detail, often writing about these mathematical questions in poetry. So you can imagine the very first question that would naturally come up. If you're composing poetry, so say you know your long syllables last 2 beats, your short syllables last 1 beat. Natural question that comes up, if you're composing poetry, you have 8 beats of poetry left that you need to fill. How many ways can you fill in those 8 beats with longs and shorts? If a long is 2 syllables and a short is 1 syllable. So how many rhythms or how many poetic meters can one construct of 8 beats consisting of long and short syllables, where a long syllable lasts 2 beats, a short syllable lasts 1 beat? So this is a question that was raised already back in at least 300 BC in ancient poetic works. Okay, so, well, if we have 8 beats, and we need to fill them with long and short syllables, where long is 2 beats, short is 1 beat, what are ways that you can fill in 8 beats? Well, you could go long, 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 long. That'll be 8 beats. Or you could go short, 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 short. But then you can do various things in between. Right? You can do short, long, long, short, long. Long, long, short, short, long. And so on. So what are the total number of ways that you can fill in 8 beats with longs and shorts? Natural mathematical question that first came up in the context of poetry back in 300 BC. So phrased more mathematically, what is the question that's being asked? We're asking how many ways can one write a number n was 8 in that case, as a sum of 1s and 2s. Right? We can write it as 2 plus 2 plus 2 plus 2, that's the long, 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 long. Or we can write it as a sum of 8 1s, or various combinations in between. Order mattering, because this is music, this is poetry. Well, the way that mathematicians would approach this question, this is the way the poets approached this question, back in 300 BC, is to work out the first few examples, understand the pattern, formulate a theorem, and then prove the theorem. And this is exactly what happens in these ancient poetic works. So n equals 1, okay, well suppose you just have 1 beat of poetry left. How many ways can you fill that in? Okay, well there's no room for a long, so you can just do a short, and that's the end of that. So there's just one way. If you have 1 beat of poetry left, that's all you can do, you have to do a short. Okay, but if you have 2 beats of poetry left, there are 2 things you can do. You can fill it with a long, or you can fill it with 2 shorts. You can do short, short, or you can do long. So there are 2 ways of filling in 2 beats. If you have 3 beats left, well, you can do 3 shorts, you can do long, short, or you can do short, long. So there are 3 ways to do that. If you work out all the ways that you can do 4 beats, you can do 4 longs, you can do 1 long and 2 shorts in 3 different ways, or you can do 2 longs. Okay, if you work it out for 5 beats, how many ways can you fill in longs and shorts? Turns out, well, those are all the ways that you can do it. And you see there are 8 ways. Okay, so that's the pattern of numbers. That's the pattern of numbers that you get. And so what's the general answer? So after this is worked out in ancient poetic works, a general answer is formulated. And it's written in this beautiful poem that describes how you figure out the number of ways of filling in n beats for general n. So just translating the poem just has 2 lines. It says, the first line is, write down the numbers 1 and 2. And then the next line says that every subsequent number that you write down should be obtained by adding the previous 2 numbers that you wrote down. And then if you look at the nth number in the resulting sequence, that will give you the number of poetic meters of longs and shorts having n beats. Okay, so let's try that procedure. So you write down the numbers 1 and 2, and then each subsequent number will be the sum of the previous 2 you wrote down. So 1 plus 2 is 3, 2 plus 3 is 5. Last 2 numbers are 3 and 5. They add up to 8. 5 and 8 is 15. 8 is 21. 13 plus 21 is 34. 21 plus 34 is 55, and so on. And that's the sequence that's produced. And if you want to know the number of rhythms having 8 beats, well, you just count 1, 2, 3, 4, 5, 6, 7, 8. The 8th number in the sequence, that's 34. And so the number of rhythms having 8 beats, turns out there are 34 different rhythms having 8 beats, consisting of long and short syllables. So there are 34 rhythms having 8 beats. So these numbers by ancient Sanskritists, they're called the Virahanka numbers. They're also called the Hemachandra numbers. I'll explain why in a second. So these are called the Virahanka numbers after the linguist Virahanka, who's a poet, the year 700, who first documented them and proved their recurrence property. The fact that they're generated in this way where you just keep summing the previous 2 numbers that you wrote down. So this is the first reference that's known of these numbers. But these numbers were also written about by Gopala in around the year 1135, and then by Hemachandra in 1150, who really wrote about them very extensively. And so they also got to be known as the Hemachandra numbers. But reading literature, you really find that the Virahanka in the year 700 really wrote about them in a pretty complete way, with an explanation of why this sequence gives the right answer. And so that's why they're also now known as the Virahanka numbers, after the first person who came up with these. Of course, these are also known as the Fibonacci numbers in the West, after the Italian mathematician who talked about these about 500-600 years later. So Fibonacci was, but this shows that Fibonacci was not the first person to write about these numbers, nor was he the second or the third. Ironically, in India, they're also called the Fibonacci numbers by mathematicians. Not the linguists, of course, we call them the Virahanka numbers or the Hemachandra numbers, but among mathematicians, you can see that this divide has developed between the humanities world and the mathematics world. The mathematicians actually, even in India, call them the Fibonacci numbers. So that connect that used to be there back around the year 1000 and before and after, that split has occurred, and it's kind of unfortunate because the connection between poetry and mathematics that this illustrates, and there are a lot more, I'll mention some more, is very rich, and it's actually a very nice way of teaching about mathematics through poetry and vice versa. For example, when we learn about Fibonacci numbers nowadays, it's through this incestuous story about rabbits that has no basis in reality. Whereas this is how this story is how they originally came up, and it had an actual practical application to poetry that poets were actually interested in, and that's how these numbers were originally discovered in the conscience of poetry. Much more beautiful, and for a way of learning in school, that connection would be nice to restore. So why does Virahanka's method work? So he has one poem about that as well. And the poem, it's a one-line poem that explains why it works. He says, well, notice that every rhythm ends in either a long or a short. Therefore, the method works. Okay, so you have to unwind that a little bit. And this was an attitude, it's called the Sutra style in Sanskrit, where you just give one line and you're supposed to unravel it to understand what it means. But why is this a proof that works? Well, yeah, he's made the main observation there, is that every rhythm ends in a long or a short. So what does that mean? Well, okay, so every rhythm ends in a long or a short. So suppose you need to make an n-beat rhythm. You observe that it has to end in a long or a short. If it ends in a short, then there are n minus 1 beats left that you have to fill in. If it ends in a long, there are n minus 2 beats that you have left to fill in. So therefore, the number of rhythms having n beats is the number of rhythms having n minus 1 beats plus the number of rhythms having n minus 2 beats. And that's why you have to keep adding the previous 2 numbers. So think about that. It's written in a very compact way. But the point is, if you let Vn be the number of rhythms having n beats, then you break that set of rhythms into two piles. The first one where it ends in a long, and the other one where it ends in a short. And if it ends in a short, the number of ways of filling in the rest of the beats, the n minus 1 beats, is Vn minus 1. If you look at the set of rhythms that end in a long, then the number of ways of filling in the remaining n minus 2 beats is Vn minus 2. And so therefore, the nth element of the sequence has to be the n minus first element of the sequence plus the n minus second element of the sequence. So it's just, the proof is very elegant. It's just that you just need that one observation that everything ends in either a long or a short, and that implies the recurrence formula that you were looking for. So of course the Vierhanke or the Fibonacci numbers, they now form the basis of a huge mathematical and artistic theory. There's a whole journal dedicated to these numbers. But they first, so these numbers are very, very important. They're important, of course, in poetry, where they first arose. But they're important in the visual arts, in architecture. And my favorite place where they arise is, of course, in nature's art. So there's a whole journal dedicated to these numbers. Now, but it's just interesting to note, especially today, that these numbers actually first originated in poetry. In case you haven't seen the examples of where these numbers appear in nature's art, if you look at a daisy, the number of petals on a daisy tends to be one of these numbers. So here's an example of a daisy which has 13 petals, and its whole species, they all have 13 petals, for the most part. Here's an example of a daisy that has 21 petals. And this is one of my favorite pictures. There's a whole garden of daisies, and all these daisies have 34 petals. And I know that because I actually sat there and counted them. But there's that number 34. I think that's really beautiful because 34 was first written about in the year 700 in the context of poetry. But of course, nature knew about that number 34 way earlier and made gardens of daisies full of 34s. But that's something that mathematicians always love. That's one of the things that's very poetic about mathematics, the union, right? The unity of mathematics, that you ask a question about what's the most efficient way of making flowers. So why does this happen that you get 34? That's only recently been sort of understood. It's not understood in the sense of the way mathematicians like to understand something with a rigorous proof, but there's a basic understanding of why daisies tend to sprout a Vierhanke number of petals. It has to do with the fact that the petals are sprout from seeds within the center of the flower, which grow in a spiral. And what is the most efficient way of packing seeds in a spiral? It turns out it involves something called the golden angle. You always want to turn by a golden angle when you're growing these seeds to pack them in as efficiently as possible in the center. And after an integral number of rounds, you always get one of these Vierhanke numbers or one of these Fibonacci numbers. That's something really amazing, that you have this kind of unity between the question, what is the best way of, if you have 8 rounds of seeds growing in a flower, you get 34 petals. If you're asking about rhythms having 8 beats, well, there are 34 ways of making rhythms having 8 beats. That kind of unity of mathematics is the kind of poetry that really excites mathematicians. The 34 appears in both contexts in that way, for reasons that are not completely obvious until you look into it and then you see, oh, it's the same reason. So for me as a musician, these numbers come up very, very often. I wish I'd brought my drums, but I brought an audio clip of my teacher playing. So a lot of times in Indian classical music, a lot of Indian classical music is based on the ancient rhythms of Sanskrit poetry. They evolved into methods of improvising in classical Indian music. And a lot of times you'll have in a piece this dichotomy between long and short. You'll have 2 phrases, one of which is exactly twice as long as the other. And you're improvising in a certain rhythm cycle that may have 8 beats. We'll have 8 beats, so that, well, we have 34 different possibilities that you can fill in on each of the 8-beat measures. And that sounds like, okay, well, there are only 34 things you can do. But actually, well, music is all about how to create complexity from simplicity. And there's actually the combinations in which you play those 34. So the art of, wow, it's getting louder. Yeah, thanks. The art of playing drums, in large part, is first to know what combinations you have at your disposal. Kind of like a painter needs to know what colors they have at their disposal, but then how you use them, how you emphasize the left hand and right hand, in what order you play them to tell a story. There's a lot of complexity in that, actually. So first there's the mathematical side of knowing what your repertoire is, just when you are restricted by that dichotomy within a certain number of beats in each measure. But then the second aspect of the art is to understand in what order to play things in a particular part of the music that will really tell the story of that piece. So in this piece that I'm going to play now, which is my teacher, Ustad Zakir Hussain, playing exactly 2 phrases. The whole piece is only 2 phrases. One is dhati gene, and one is dhine. So dhati gene is twice as long as dhine, and he's just going to play combinations of those. He's going to start with dhati gene, dhati gene, dhati gene, dhati gene, which is the 4 longs, and then he'll move into introducing shorts gradually in a way to tell a story. So let's see if I can play this. I'm saying it much slower than he's going to play it. So it's going to be that speed. So that entire piece with only 2 phrases being played the whole time. And you can't really tell. It's being played so fast in so many different combinations, it sounds like incredibly complex things are happening. And yet the whole, the magic of that is that from absolute simplicity, just playing 2 phrases, that complexity is created. And of course the core knowledge in that is to understand how to navigate your way through those 34 combinations of filling in longs and shorts into 8 beats. So I want to mention a couple other questions that naturally come up in this context of longs and shorts that led to discoveries of other major mathematical objects. Instead of asking how many rhythms you have having 8 beats, another natural question to ask is how many rhythms do you have having 8 syllables, okay, where you have a given number of longs and a given number of shorts. Okay, that's a different question. Right? So for example, you could ask how many 5-syllable rhythms are there in which 3 of them are long and 2 of them are short. These are also, so some rhythms in classical Indian music are classified just by the number of syllables, but some are classified by not just the number of syllables, but among those syllables, how many of them are long and how many of them are short. That may be a further constraint when you're writing a poem. And the answer, well, the total number, if you're not putting any restrictions on how many longs and how many shorts there are, well, that's just a power of 2. If you're going to have n syllables, the total number of combinations of longs and shorts is 2 to the n. But now, if you impose the condition that, say, k of them are short and n minus k of them are long, that now restricts your repertoire. It also fixes the number of beats, but it's doing more than that. It's not just fixing the number of beats, it's also saying, I'm specifying how many longs and how many shorts there are going to be. And that, of course, was also an important question for a certain class of meters that poets were writing in. And so, in Sanskrit, short is called laghu, a long is called guru. So, often use L and G for short and long. So if you consider, say you have just 3 syllables. Over here, you have the situation where there are 3 longs, 3 gurus. Here you have the situation where there are 2 Gs and 1 L. Here you have the situation where there are 2 Ls and 1 G. And here you have the situation where there are 3 Ls. In total, there are 8 as we said, 2 times 2 times 2, but they're classified by how many G's there are and how many L's there are. And the pattern there is 1, 3, 3, 1. Okay? There's one combination where all 3 are gurus. There are 3 combinations where 2 are gurus and 1 is lagu. There are 3 combinations where 2 are lagus and 1 is guru. And there's one combination where 3 are lagus. And so these numbers you may recognize as well. These are called binomial coefficients nowadays, but these were first written about in about 300 BC by the great Sanskrit poet and linguist Pingala, who gave a complete solution to how to calculate the number of combinations for any number of syllables n. And in fact, his writing is what motivated Virahanka to come up with his sequence. And I'll show you why. So his general answer is also written in a poem, and his poem is as follows. Write down the number 1. And then each subsequent number that you write down should be obtained by adding the 2 numbers immediately above it. So he writes that in 2 lines of poetry. And he says what results is a mountain of jewels. The jewels being the numbers. He calls it the Meru Prastar, which means expansion of the mountain of jewels. Which is kind of a very poetic name for a mathematical object. So how does this work? You write down the number 1, and then each subsequent number you write down will be the sum of the 2 immediately above it. So this 1 here is the sum of this 1 and this blank over here. And this guy here, that's going to be 1 also, because it's the sum of this 1 and this blank. Now in the next line, this 1 is the sum of this blank and the 1, but this 2 here is the sum of this 1 and 1, the 2 numbers above it. And this 1 is here is the sum of the 1 and the blank. In the next line, right, this 3 is the sum of the 1 and 2 above it, this 3 is the sum of the 2 and 1 above it, this 1 is the sum of the 1 and blank above it, and so on. And so you get this expanding mountain of jewels, which is exactly what he called it, the Meru Prastar. And now if you want to know the number of rhythms having a given number of syllables and a given number of shorts and longs, well, suppose you're talking about 3 syllables, you go down to the 3rd row, 1, 2, so, sorry, 1, 2, 3. And then if you want to make sure that it has, say, 1 long and 2 shorts, well, if it's 1 long, you move in 1, and there's the answer, 3. So that's how this mountain of jewels is used. So there it is. So for example, if you want 2 longs and 1 short, there it is. If you want all combinations of rhythms where you have 3 longs and 2 shorts, then it's going to be 10, and so on. So this is called Pingala's Meru Prastar. It was discovered back in 300. So why does Pingala's method work? Well, it's essentially the same reason. So I want you to think about that. So if you're trying to count all rhythms that have, say, k shorts, n minus k longs, why does this procedure where you keep adding the 2 immediately above it, why does that work? The answer is the same. It's a one-line answer, namely, well, if you have an n-syllable rhythm with k longs and n minus k shorts, well, any such rhythm has to end in either a long or a short. And then you group it into those 2 categories, and you'll find that those 2 numbers that you're adding immediately above it correspond to those 2 groups. And that's what leads to this recursion. So in modern notation, for the mathematicians, if n choose k denotes the number of let's just say n syllable. If n choose k denotes the number of n syllable rhythms having k short syllables and n minus k long syllables, then n choose k is going to be n minus 1 choose k minus 1. So if n choose k, right, if the last syllable turned out to be short, then this is how many things you have left to fill in. If the last syllable happened to be long, this is how many you'd have left to fill in. So just think about that. I went through that very quickly, but it's really just that same line argument. So this is also, so these numbers are called binomial coefficients, and this expanding mountain of jewels is also called, in the West, Pascal's triangle, after the French mathematician who lived 1800 years later. And again, it's also true that the mathematicians in India call it Pascal's triangle. Same disconnect. It's there. But it's called Pingala's Meru Prastar by Sanskritists and linguists. Well, these entries of the Meru Prastar are called binomial coefficients, and of course these are some of the most important objects in all of mathematics now. They play an extremely important role in statistics and combinatorics and number theory. basically in every branch of mathematics. They're fundamental to almost every subject in mathematics now. And I love to be able to say that they were first discovered in the context of poetry. That's the theme of today, but it's not just that there's a connection. These numbers, fundamental to all of mathematics, were actually first discovered by poets for their applications. So the recap is, if you count rhythms and meters having a fixed number of beats, that yields the Virahanka, or Fibonacci numbers. And if you're counting rhythms and meters having a fixed number of syllables, with a given number of longs and a given number of shorts, that yields Bingel's Meru Prastar, or Pascal's triangle. And these are the contexts in which these two fundamental objects of mathematics were actually first discovered. Now, given that they both involve counting rhythms and meters, they're very similarly phrased, you might wonder, well, how are these two related? And this is also, how are these two mathematical objects related? This is also something that was written about by ancient poets. And instead of sharing the poem, you can just see visually how that's happening. So you make the Meru Prastar, this mountain of jewels, and if you sum the numbers along the shallow diagonals, you exactly come up with the Virahanka numbers. So if you sum along this shallow diagonal, 1 plus 5 plus 6 plus 1, gives you the 13. So those two mathematical objects, this is again one of those things that mathematicians love. You have two different questions that sound different, and then you see what the connection is later on of different mathematical objects. This is another thing that really excites mathematicians, but it also excited poets back in the day. The connection between two different mathematical objects. So I urge you to think about, just in terms of rhythms, why this is true. If you sum along shallow diagonals, why do you have the Meru Prastar, why do you get the Virahanka numbers? So why, when you're counting meters having a given number of beats, that involves summing together the number of rhythms having a given number of syllables with a given number of longs and a given number of shorts. If you just think of it in that way, you'll see immediately that this has to happen. So that's the relation between those two mathematical objects. So here's another exercise that comes up. What happens if there are three kinds of syllables? Okay, short, long, and extra long. There was actually a name for an extra long syllable in the Sanskrit literature. It's called plut. So these are laghu syllables, these are guru syllables, and these are plut syllables. And actually, in around the 1100s and 1200s, there was a treatise by Narayana where he said, well, let's just look at the general situation. What if you're playing music and you have phrases of length 2, 3, and 7, or just general? You have a set of phrases, and you want to know if you have 100 beats, how many ways can you fill them in? And he developed a theory of recursions just based on counting the number of rhythms having different number of musical phrases. This is the first case that he considers where instead of just using 1 and 2, you have 1, 2, and 3. A phrase of length 1, a phrase of length 2, a phrase of length 3. How many musical pieces can you make of a given number of beats having these three phrases? And the answer to this particular question, the analogs of the two questions that I asked, how many rhythms are there having a given number of beats, how many rhythms are there having a given number of syllables, the answers are given by the Virahanka, or Fibonacci numbers. It's the same joke in both languages. And there are actually lots of papers about these numbers that have been published. They're well studied. And for the other question, you get a three-dimensional Meru Prastar, a three-dimensional extension of a mountain of jewels. Well, since we live in a three-dimensional world, this is really the true mountain for our world. Here's what it looks like. So if you can imagine, right, this is a three-dimensional pyramid that's going off to infinity towards the bottom. And each layer is made, each number is the sum of the three numbers immediately above it. So for example, this 6 here is the sum of the 3 2s above it. This 3 here is the sum of this 2 and this 1 and this blank, and so on. And you get this mountain, a three-dimensional mountain of jewels that goes off to infinity below. And so, for example, if you want to know how many rhythms there are having 5 syllables, in which 2 are short, 2 are long, right, and 1 is extra long, well, what do? You go to the 5th layer, 1, 2, 3, 4, 5, and then you work. Musicians want to be able to, if they want to communicate with each other, they want to say, play the 7th rhythm with this constraint. And they had a way, an algorithm. So enumerative algorithms first originated in the context of poetry, where not only were they saying this is the total number of waves, but they had a way of listing them in a systematic way. And if two musicians met and they said, we were going to play the seventh one of these constraints, they would both agree what that is. And they could just say that on stage and start playing in that rhythm. So the notion of not just counting, but enumeration was very important at that time. And Donald Knuth writes extensively in his Art of Computer Programming about a lot of these enumerative algorithms that were first discovered in the context of poetry. Okay, so I'll end with one last example of how poetry led to beautiful mathematics. This is one of my favorites. One I found most mind-blowing when I was growing up and learning this from my grandfather. It's about this powerful nonsense word, which I just loved saying as a little kid, and then only gradually did I learn how to use it. So here's the word. Yamata Rajibhana Salagat. That's the word. And what does it mean? Well, it doesn't mean anything. Yet every poet and every musician learns this word in South India. They still learn it in the Kerala region, and all Sanskritists, of course, still learn this word. So it's Yamata Rajibhana Salagat. And I've indicated which ones are long by the bar. Okay. So when you're pronouncing it, the long ones are pronounced twice as long as the short ones. So if you pronounce it, it goes Yamata Rajibhana Salagat. So I put zeros for the shorts and ones for the longs, which is confusing because the one is exactly twice as long as the zero. But this is the system that was sort of used in the ancient texts because they thought of it in terms of binary. And so there's a lot of 0 and 1. Okay, so why, if it doesn't mean anything, why does everyone learn this word? Well, there's something very special. So if you write 0 for all the shorts and 1 for all the longs, there's something very special about the sequence of zeros and ones. You want to see what it is? So there's something very special about the sequence of zeros and ones. What's happening, suppose you just look at consecutive triplets in the sequence of zeros and ones. What do you notice? It turns out that every triplet of zeros and ones, every possible triplet of zeros and ones, is swept out and occurs exactly once. So there are 8 possible triplets of zeros and ones, and you'll see that they all occur as consecutive triplets inside the sequence. So you have 0, 1, 1, right? And then you have 1, 1, 1, right? Then you have 1, 1, 0. Then you have 1, 0, 1, 0, 1, 0, 1, 0, 0, 0, 0, 0, and 0, 0, 1. So those are 8 triplets, and you'll notice that they're all different and every single one occurs. This is the shortest possible sequence that you can make that has every possible triplet, because each one is occurring exactly once there. So that's what's special about that word, is that it allows you to remember this sequence of zeros and ones, where each triplet is swept out exactly once. If you start with 0, 1, 1 and try to make such a sequence, it turns out there are only 2 solutions. And this is one of them. So there's an exercise, find the other one. This is one of 2 possible sequences where you start with 0, 1, 1. You always have to start with something. You start with 0, 1, 1. No matter what you start with, there will be 2 solutions on completing it so that every triplet arises exactly once. And this is one of those solutions, and everybody memorizes it. They've decided that this is going to be the one they remember, and that gives you a common language now. Okay, so that's what's special about that word. And one thing you notice about it is that it begins with a 0, 1 and it ends with a 0, 1. So if you decided that you wanted to think of it as a circle instead of a line, right, this 0, 1, if it wrapped around, would overlap with this 0, 1. And that's often talked about as the snake eating its tail. So here's a snake with the Yamata Rajibhana Salagat written on it. And if he decides to eat his tail, this 0, 1 will overlap with this 0, 1. So right, there he goes. He's going to eat his tail. This one, these ones will overlap, and these zeros will overlap. And there he goes. And now the sequence of zeros and ones, as you go around, there are only 8 zeros and ones here, so there are 8 triplets that are consecutive on the snake, and each one is different. So there are 8 possible triplets around the snake, and every possible triplet is swept out and exactly once. Okay, so what is the use of this word? So why does everyone bother learning this word? Yamata ra jabhana salaga. Well, the purpose is that this word yields an efficient mnemonic for remembering long rhythms. So it gives a common language, a common way of making mnemonics for remembering long rhythms. So how does that work? Well, basically you just use these consonants. And each consonant represents a triplet, namely the triplet that starts there. Right? So if you just look at ya stands for 0, 1, 1. You just take the triplet that starts there. Right? Same way ma means 1, 1, 1. 1, 1, 1. Right? All 3 longs. Da means long, long, short. Right? 1, 1, 0. And so on. And so we have one letter, one syllable that represents every possible triplet. And so, well, yeah, so the idea was, you break up if you have a really long rhythm that you want to remember, you break it up into triplets, and then each triplet corresponds to a consonant, and then you can interpolate vowels through there to make phrases that will then represent long rhythms. So here's a very non-traditional example. So if you take the word tiramisu, that corresponds to a rhythm. And what rhythm does it correspond to? Well, the T represents, 1, 1, 0. The R represents 1, 0, 1, right? The M represents 1, 1, 1, right? And then the S represents 0, 0, 1. Right? So 1, 0, 1, 1, 1, 1, 0, 0, 1. Another non-traditional example. Right, if you take Yosemite, what does the Y represent? 0, 1, 1, right? Y represents 0, 1, 1, 0, 1, 1. The S represents 0, 0, 1, and so on. M represents 1, 1, 1, the T represents 1, 1, 0. Okay, now what happens if, well, suppose your rhythm is not a multiple of 3 in length. Then what do? Well, then you're going to have some stuff left over, right? You're going to have some longs and shorts left over. Well, notice that you also have 2 things left over here. Right? There's a triplet starting at S, but there's no triplet starting at L, and there's no triplet starting at G. So the L is used to just represent the singleton 0, and the G is used to represent the singleton 1. So it just works out perfectly. So terminal would be, well, T represents 1, 1, 0, R represents 1, 0, 1, M represents 1, 1, 1 again, N represents 0, 0, 0, right? And then you have the singleton left over, and that represents a single 0. The L and G were chosen carefully. Remember, laghu stands for short, and guru stands for long, and so that's why they were used there at the end. And that's why they chose the triplet to end in 1 short and 1 long. They could have end in 2 longs, but then this wouldn't work. So this was a mathematical constraint that they needed the last 2 syllables to be different. And then they made 1 stand for laghu, 1 stand for guru. The other trick that's involved is that you don't always have to break up the triplets and then just have the L or G left at the end. You can have singletons in between. You can be clever in how you break it up into triplets and singletons so that there is some word or phrase that goes through them so that it's easy to remember that long rhythm. So for example, regal, the R represents 1, 0, 1. Sorry. Go away. Yeah, 1, 0, 1. And then the G represents the long, and the L represents the short. So there you have a 1, 0. So this has been used by South Indian musicians for a long time. You often will see situations where you have 2 South Indian musicians meet on stage for the first time, and one will whisper a phrase into the other one's ear, and suddenly they're playing these complicated long rhythms in unison. And everyone's like, how on earth did they do that? They just met, and they're playing these incredibly complex long rhythms. Well, they've internalized this word so well that if somebody says a phrase that only involves these consonants to the other one, they immediately feel, well, they immediately see that translation of the consonants into that. They immediately unwind it into that long rhythm, and they can play in unison on the spot. And so if you've ever seen 2 musicians meeting for the first time and just playing a long rhythm, this is how they're doing it. They have this mnemonic that's common to them. They just need to say that phrase, and suddenly they can play these long rhythms together in unison. So why did this word first arise? This is used by musicians much later on. But in 300 BC, and even earlier, the reason that this word came up back then was, well, it was composed by poets who wanted to preserve the integrity of their rhythmic compositions. So this is a situation that you might find yourself in. You compose a new rhythm consisting of longs and shorts. It's very long. And, well, you want it to be preserved forever. You want that rhythm that you composed, you want it to be preserved forever. Now, how can you do that? You sell it to the next generation, and they might flip a bit, and then by the time, 2,000 years later, it's completely different than when it started. Right? You've all heard the game telephone. You keep telling the next person, and by the time it comes back to you, you don't recognize it. So, for these poets, their compositions, the integrity of these compositions was very, very important. And so they wanted a way of, after they had composed a new rhythm, a new meter, they wanted a way of preserving it for all posterity. And the way they came up with preserving it forever was truly ingenious. So the ancient poets composed hundreds of original and beautiful rhythms, and talas. Talas are rhythms that are used in music. In poetry, you call them meters. And they wished to preserve them without even a single error, forever, so that people could play compositions in exactly those rhythms that they composed forever. But of course they understood that this would be difficult because at that time they weren't writing, these were transmitted orally from generation to generation, and it's easy in oral transmission for bits to start flipping. So this was their ingenious solution to the problem, which allowed hundreds, probably thousands of rhythms that are still preserved exactly intact until today. And their ingenious solution was as follows. They used this word, Yamata Rajamhanasalega, in a really ingenious way to preserve their compositions for posterity. So how do they use this word to preserve the integrity of their rhythmic compositions? So as a result, 3,000 years later, we still have their compositions intact exactly as they had composed them. So this is how they did it. What they did is, after they had this rhythmic composition that they were proud of and they wanted to preserve, what they did is they wrote a poem in that rhythm about the rhythm. And then moreover, so already it's an acrobatic act that you want to write a poem about the rhythm, and you have to write it in the rhythm that you're writing about. Okay, so that's the first acrobatic act. But in addition, inside that rhythm, they put the encoding using the word Yamataraj Bhanasalaga, right, into triplets, right? Remember, where there's a way to encode the rhythm. They put that encoding within the poem. So this is a really acrobatic act. You're writing a poem in the rhythm, about the rhythm, with the encoding of the rhythm using Yamataraj Bhanasalaga, all inside that same poem. And if you succeed in doing that, it's going to be really hard to flip a bit and have all those constraints satisfied. Because the encoding would go wrong, the poem's description wouldn't match the rhythm that's there, okay, all sorts of things will go wrong. So here's an example of one such rhythm that's very popular. It's called Shardula Vikriditam, which means the play of the tiger. So I'll sing it for you. So it goes, Suryashvai Yadima Sajo Satatgah Shardula Vikriditam. They all came with a tune also. So if the tunes were also transmitted generation to generation. So again, if a bit was flipped, it wouldn't match the tune either. So that was another level of making sure that everything stayed the way it was composed. So the translation is, if there are 12 plus 7 syllables, in the form ma sa ja sa ta ta ga, right? So if, this is if, there are 12 plus 7 syllables in the form ma sa ja sa ta ta ga, then it's called Shardula Vikriditam, the play of the tiger. Okay, so there it is. So there's a poem about the play of the tiger. It's, well, if there are 12 plus 7 syllables in this form, then it's known as the play of the tiger. So that's the poem about that rhythm, and it's in that rhythm. So here I'll put the longs and shorts there. So if I sing it again, I'll clap it for you. So Suryashvai Yadima do, sa, da, do, da, sha, do, li, do, do. That's the rhythm, the play of the tiger that I just clapped. And so here's the magic of it, is that, well, you have the ma, sa, ja, sa, ta, ta, ga here. What does ma mean? Remember, ma means long, long, long. There it is, long, long, long. What does sa mean? Well, sa means short, short, long. And there it is, short, short, long. So if you unwind this ma, sa, ja, sa, ta, ta, ga, it covers this entire, right? If you unwind just this part, it covers the whole poem correctly in its longs and shorts. And so as a result of that, if you flip any bit here, there'll be an internal contradiction about the constraints that it's supposed to satisfy, and that's how it's been preserved all these years. And it's actually, this particular rhythm has become one of the most popular rhythms in which poets composed over 2,000 years. Maybe we'll try clapping this together. I'll do it once for you, and then we'll do it together. Okay, so just watch the ones and zeros, longs and shorts. Okay, so I'll do it once. So, ready, set, go. Does everyone see the longs and shorts, along with the ones and zeros? Okay, ready, set, go. Try one more time. Ready, set, go. Pretty good. Pretty good. We got better. The end is a little bit more difficult, but it started out very good. Yeah, so that's how this rhythm has been preserved all these years. I'll give you one more example. So this is called Bhujanga Prayat, which is called the gate, in other words, the gate of the cobra. So when you see a cobra move, it kind of, it doesn't go evenly like this, but it goes in jerks. So it goes, and so Bhujanga Prayatam, the rhythm is, right, so you're hearing this. So you're supposed to feel the gait of the cobra there. That was the observation of the poet, and he wanted to make a poem based on the movement of the gait of the cobra. And so that's his composition, 0-1-1, 0-1-1, 0-1-1, 0-1-1. And his poem about it is the gait of the cobra, Bhujanga Prayatam, consists of a quadruple of yas. Right, remember ya means 0-1-1. So his poem is Bhujanga Prayatam Chaturbhir Yakare. Bhujanga Prayatam Chaturbhir Yakare. And here's his poem about it. The gait of the cobra consists of a quadruple of yas. He couldn't say ya, 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 ya. That wouldn't fit in the poem, right, in the rhythm. So these are the acrobatics that they have to do. If you say quadruple of yas, you can have it fit into the rhythm. So Chaturbhir means quadruple, 4 times. Yakare means ya, right, sequence of yas, a quadruple sequence of yas. And that's Bhujanga Prayatam, the gate of the cobra. So there's the poem about the quadruple of yas. And there was a tune associated to it, so now this was preserved for all posterity for thousands of years. If you flip a bit, it wouldn't be consistent, internally consistent. This one I think will be easier to clap. Ready, set, go. We want to get it perfect? Ready, set, go. That's the gate of the cobra. So that's one more example. There are hundreds of examples like this of poems that are composed about the rhythm, written in the rhythm, with the encoding of the rhythm. And as a result of that, we have all of these rhythms intact thousands of years later, and we know how to sing all these ancient poems. So what's really happening here? This is kind of an error-correcting, error-detecting code, right? For poetic rhythms. This is perhaps the very first and very sophisticated, right? Poetically very sophisticated. I mean, it's not an error-correcting code in an exact mathematical sense, that it is it's a poetic error-correcting code. There are poems written about it that ensure the integrity of data, the data being the sequence of zeros and ones that needed to be preserved for thousands of years. So this is perhaps the very first and very sophisticated use of error-correcting and detecting codes in history, originating at least as far back as 300 BC. And the work of Pingala. But Pingala writes in his manuscript in 300 BC that he's collecting together the rhythms of many, many other poets over generations. So this goes back way before 300 BC, but first collected in one place by Pingala, the same person who wrote about the Meru Prasthana. Other applications of this idea, right? The fact that you have the sequence where every triplet is swept out exactly once. That's been used in modern times in searching algorithms and technology involving data wheels. So actually the very first technological use of Yamata Rajapana Salaga was in the early 20th century. It was used to make dimmers for lights. So you can imagine that you have, well, just imagine the snake. It was made like the snake, right? You can imagine the zeros and ones being on and off, right? On and off switches. And there's a sensor that just detects 3 consecutive ons and offs. And as you turn the snake, right, the dial, that sensor will see a different triplet in each position. And so in that way, the dimmer knows exactly what position it's in just by having a sensor that detects just the side. And that's how some of the first dimmers were made. It was just making that sequence of zeros and ones around, and it would just read that sequence of triplet on one end. It would just read that, and that would be enough to know the position of the dial. And this was used for other searching algorithms involving data wheels in more sophisticated ways, where you didn't just use triplets, but you used quadruplets, quintuplets, and made appropriate sequences. A very sophisticated use of it was done on NASA missions when you wanted to know the position of a satellite. On the satellite, instead of using triplets, they used, I think they used 64, how do you say, 64 tuples? So they made a big sequence where every sequence of 64 was different all the way around. And now, and they made on and offs in that sequence. And now of course, when you're looking at it, you can only see one side of it. But if you just see 64 consecutive ones, that's enough to know its rotational position, because each set of 64 tuples was different all the way around. So that was a generalization from triplets to 64 tuples that allowed one to determine the rotational position of satellites. But again, it's very cool to know that these very sophisticated ways of determining positions of wheels first originated in the context of poetry. So finally, the last one I want to mention is card tricks. There's some brilliant card tricks based on this, which of course I learned from Percy. So I was telling Percy about this word, Yamata Rajapana Salaga, and he was immediately very excited. And he comes back later and tells me there's a brilliant card trick based on this. The card trick is as follows. You have a deck of cards, you give it some cuts, and you have 5 people take off a card, and then you ask them to concentrate, and then you say, I feel red better than I feel black. Can the people with red cards stand up? And then he names their cards. And so you can think about, well, how does that work? Okay, he had people take out 5 cards from the deck, and then he knows which ones are red and black, and that allows them to name their cards. You can think about how you would do that. That's Percy's invention. Card trick based on Yamata Rajapana Salaga. Brilliant card trick. So, okay, I think I'll stop there. I want to wish Barry a happy birthday. And thank you so much for all your inspiration. Look forward to decades more of things from you and your inspiration and your encouragement and your productivity. Thank you so much. Yeah, thank you. I'm happy to take questions, by the way. maybe a couple. Yeah. Sure.
In the art of sound poetry, is there a connection between the semantics and the rhythmic patterns? That is, the rhythmic patterns somehow carry it?
Yeah, so the question is there a connection between the rhythmic patterns and the semantics? And absolutely, yeah. So the rhythmic patterns were deliberately named after a mood, the play of the tiger, the gait of the cobra. Some of them were named explicitly after moods. So the purpose of the rhythms was to evoke a certain emotion, and certain words and certain kinds of themes that you would write about would feel better in certain rhythms. And that's how one chose which rhythm to write in based on what you were writing about, because that would help bring out the feeling of that particular poem correctly. Yeah. Yeah.
Are there certain rhythms, even though when you calculate the number of possible rhythms, are there certain rhythms that are simply not played because they don't sound right? Drummers, will never play long.
Yeah, absolutely. Yeah, so there's, there are a lot of aesthetic considerations, and I mean, there's a reason why only certain ones are named and certain ones you just don't, you're not interested in propagating. That's the aesthetic aspect of this, right? So there's an aesthetic consideration when one improvises, when one is playing music, and in the same way when one is composing meters. There's definitely a big aesthetic consideration when composing, yeah, and when playing. Yeah, absolutely.
So it's more of a comment. So this long consensual work is basically a De Broglie sequence
right.
of triplets, and there was a very nice application of this in biology, since we started listing this.
Oh, yeah.
So there was one problem where you want to find where a particular protein binds to DNA, and you want to design a sequence of DNA that contains all K-mers of a particular kind of in the shortest possible way, and usually this is done with 7 mers or 10 mers. And so people employ Broglie sequences to design such DNA platforms that probe where the protein binds. It's not here at the Harvard Medical School.
Oh, really? Oh, that's so cool. Very cool. Wow, very nice. Yeah.
Do I understand correctly that there's a Barry rhythm in this system?
There's a Barry rhythm. Yeah, absolutely. VRR. There's also Munchel rhythm. We should play it together sometime. Yeah, okay.
So you mentioned the binomial coefficients and the Fibonacci numbers, but some would argue that in between those, the importance would be the Catalan numbers. Is there anything about Catalan numbers? Any of this?
I haven't seen it in the poetry literature, but of course, yeah, we could do it. Very, very good question. On the other hand, I have to say, most of these works have not been translated. So I've started doing some of them. I've found, in Virahanka actually, I've found all sorts of sequences that don't have names currently, that I've never really seen before. Various constraints on poetic meters, and then he creates these sequences that I've just never seen in the mathematics literature before. I haven't come across Catalan yet, but there are a number of sequences that actually I haven't seen before that are coming up there. And so there are at least 70, 80 works that have not been translated about poetic meters. So it's possible one day eventually they'll come up. But what I found really interesting is that so many sequences came up that I haven't seen in the mathematics literature before. And I'm kind of excited to know if they have cool properties from a mathematics point of view as well.
Are they on OEIS?
Some of them I've seen on OEIS. When I come up with them, I put them in. Some were not. Yeah. Or there are at least variations of things. I mean, usually you can find almost anything on OEIS, but until you put enough terms, and then it starts to disappear. Yeah.
Catalan numbers have arisen in Western culture, the enumeration of non-crossing lines.
Enumeration of?
Non-crossing lines.
Oh, right. Yeah. Right. I've seen that. Yeah. Okay, maybe one last. Oh, no more questions. Okay, well, thank you so much.